this video, we are going to explore what is meant by radar range equation. So this is one of the most important formulas in radar engineering. So this is mostly used while designing the radar system to calculate the maximum range a radar can detect. So let's explore what is meant by radar range equation. So let's start with the radar. Let's say it's a monostatic radar, that is the transmitting and receiving antennas are in the same place, and this radar is having the transmission, so it is transmitting electromagnetic waves from this antenna. So when it detects a target, it will hit on the target and the reflected wave will be coming back to the antenna. So the maximum range at which a radar can detect the target is known as the maximum detection range, or R maximum. So in this case, this R maximum actually depends upon the transmitted power. So if the transmitted power from the radar is more, the detection range can also be more, but it is not a direct relationship. We can see how it is in when we derive the radar range equation. It also depends upon the size of the target. So if the size of the target is very small, or the reflected power from the target is very small, the received power will be very small and the detected range will be less. So it also depends upon the reflected power from the target. So the reflected power from the target depends upon the size, shape, incident wave angle, and the material of this target. Another important factor which decides this maximum detection range is sensitivity of the receiver. That means the minimum power that a radar can identify as a target. That means if let's assume if the target is here, that means in the mid range, we can say that the received power will be more and this radar can detect it as a target. But as the distance increases, the received power will be getting less, and sometimes it may be detected as noise level. So the detection range actually depends upon the sensitivity of the receiver. That is, by sensitivity, it means the minimum power that a receiver can identify as the uh, target. It's very easy to derive this maximum range, because we just have to trace this path of this electromagnetic wave from the transmitter to the target and then coming back to the receiver end. So if we trace this path, we can easily derive this maximum detection range. So let's see how it is done. So consider a monostatic radar system. I'm taking this as the target, and this is my transmitter and receiver system. So I'm first assuming that this radiation from the transmitting antenna is isotropic. So we know that in case of an isotropic antenna, it will be radiating equally in all the directions. So it will look like a sphere. So in 2D dimension, it will look like this. So I'm considering the 2D, but in 3D case, it is actually look like a sphere. So that means it is actually radiating equally in all the direction. So if you want to calculate the power hitting on the target and the distance from the isotropic radiator, that is from this point to the target is R1, we know that this distance actually affects the received power on the target. So as the distance increases, the power hitting on the target will also decrease with respect to the distance. As it is a sphere, the power incidenting on this target can be easily calculated based on the power density. So if Pt is the total power radiating from this isotropic antenna and R is the distance to the target, so the power actually incidenting at this place can be given by Pt by 4 pi r square, where 4 pi r square is the surface area of this sphere, because it is an isotropic radiator. So the total power hitting on the target is Pt by 4 pi r square. So this is the case of an isotropic radiator. But we know that all the antennas are directional. Our radar is also directional, so it has a directional pattern and maximum gain in particular directions, and it has side lobes and back lobes like this. So let's say our target is in the maximum direction position and the gain at this maximum position is GT. Then the power received on this target will be equal to Pt by 4 pi r square into Gt, because we know that the power is mainly concentrated by gain Gt. So the power hitting on the target in case of this is Pt into Gt by 4 pi r square. So this correspond to the isotropic case and Gt corresponding to the gain of the directive antenna. So now we got how much power is hitting on this target. So we know this video. So it shows that when a power is incidenting on it, it will be scattered in different directions and some part of the wave will be reflected back. The amount of power which is getting reflected back is given by a term known as radar cross section or sigma. So this is an important factor. We will put a detailed view on radar cross section in upcoming videos. So the reflected wave depends upon the radar cross section of this target. So this is the total reflected power. So PTGT 4 pi r square is the total incident power on this target, and based on the radar cross section of the target, this much power will be getting reflected back. So this is the reflected power. So this is the case. So now we know that what is the reflected power from the target. And as it is a monostatic radar, it has to cross the same distance again to reach on the receiver. So it has to travel the same distance r. So if it travels the same distance r, there will also be a reduction of 4 pi r square in the returning path also. So the received power on this receiving end will be 4 pt gt sigma by 4 pi r square into another 4 pi r square term. So this is the contribution from the returning path. So this is the total power reaching back to the receiver. So this is the power reaching back to the receiver. So whatever power may be the reaching back to the receiver, the antenna will receive some part of the power based on the effective area of this antenna. So if we are getting PTGT sigma by 4 pi r square into 4 pi r square power here, only effective area will be receiving this much power. So the total power will be PTGT sigma 4 pi r square by 4 pi r square into effective area of the antenna. So this is the total power received in the antenna. So this is just the derivation which forms the basis of the radar range equation. So from this we calculated as total received power equal to Pt Gt sigma Ae by 4 pi r square the whole square. So this is the equation for the total received power. And uh, this effective area is actually related to the gain of the antenna by this equation. Effective area is equal to Gt lambda square by 4 pi. So this is the relation between effective area and gain. So if we substitute this equation to effective area, we will get this equation. So it means that received power is equal to Pt Gt square sigma by lambda square by 4 pi cube r raised to 4. So these are the equations corresponding to the received power. This is in terms of the effective area and this is in terms of the gain of the antenna. So in these two equations, you can see that the received power is inversely proportional to the R to the power of 4. So this we have to consider in radar system designs. So next is what our purpose was to, we have to calculate the maximum range a radar can detect. So if the radar is detecting the maximum range, the received power on the antenna will be the minimum. So we can substitute the received power as PR min and the detection range as R maximum. So this is just the substitution of this R and PR to PR minimum and R maximum. So this forms the basis of our radar range equation. So our purpose is to calculate this R maximum. So okay. Okay, so this now we have derived all based on considering the monostatic radar. In case of the bistatic radar, we know that the total range will be this one, that is the range from transmitter to the target and then to the receiver, as these transmitter and receiver is located at different places in case of the bistatic radar. So the total Rmax will be substituted by R1 plus R2 in case of the bistatic radar case. There is no other change. And in this case, this GT will be substituted by GT and GR. That is also the change we have to be considered. And the effective area will be effective area of the receiver. So these are the things that has to be considered while calculating the PR received for the bistatic radar. So this is the so if we want to calculate the maximum detected range, we can rearrange the equation, and this maximum detected range is given by the expression Pt gt square sigma lambda square by 4 pi cube PR minimum raised to 1 by 4. So now we get the equation for the maximum detection range. So this is how the radar range equation is calculated. So radar range equation gives an indication about the maximum detected range with respect to the transmitted power, gain of the antenna, radar cross section of the structure, and the received power. So this is one of the example that shows how to calculate the maximum detected range with respect to the transmitted power. So if you this equation says if you are upgrading a pulse radar system, if you increase the peak transmitted power by factor of 16 while keeping all other factors constant, by what factor does the maximum detection range increases? So here you are increasing the transmitted power by 16. That means that if you increase the transmitted power by 16, the R maximum is proportional to Pt raised to 1 by 4. Then R maximum will be increased only by a factor of 2. That means if you have to double the distance, we have to increase the power by a factor of 16. So this is how we are calculating the maximum range. So here you can see that this R maximum is not in a direct relationship. That is, if you increase the PT by double, R max will increase by double. It is not like that. You can see from this relation that how this R max is related to the transmitted power, received power, and gain of the antenna, etc. So this is the common equation that we usually use for designing the radar systems. I hope you get some idea about what is meant by radar range equation. Thank you for listening.